In this video, we're going to look at how we use integration in our physics class. This full disclosure is not a complete understanding of integration and how it works. You're all taking calculus or have taken calculus, so you certainly know more about integration than we will cover in this course. Just getting that out there. We are going to look at some definitions, some methods that we use for definite and indefinite integrals of various functions that will allow us to solve the problems we need to solve, specifically starting with work. Just a reminder, although we haven't explicitly taught how to use a derivative, you've all learned how to do derivatives. And we've talked about how the derivative is essentially like taking the slope of a function at a particular point in time. Using kinematics, we've thought about this, that the velocity is the time derivative of the position as a function of time, and acceleration, the time derivative of the velocity as a function of time. We will see the relationship between force and energy in this unit and the next as we go through, and then we'll also look at a couple of other things. It's also a tool we can use to find minima and maxima by taking the derivative and setting that equal to 0. We will use this tool again as well. When it comes to the next side of things, if you remember back to kinematics, other than finding the slope, we said we would often find the area under the curve. And the area under the curve is something we've done with displacement from a velocity time profile, something like this. We know that the velocity multiplied by the time gives us the change in position. And so that's the area under the curve of a velocity time graph. As we are going to find out, or you have already found out, that the amount of work done can also be found this way if we have a force versus position graph. This is specifically the work done by a spring, which has a nice linear relationship. So finding the area is relatively straightforward. It turns out that this is equal to the amount of energy stored in a spring, 1/2 kx squared. And again, more details on all of that as we go. It's fairly easy to do this with linear functions. We have triangles and trapezoids and rectangles that we can use to find various pieces. We have a positive displacement here on this velocity time graph, a negative displacement there, and so on. It's less easy when the functions are higher order than linear. If we've got a function like this, and this is actually pretty common for a force, like an impact or pushing on something, you'll see that your force increases and then decreases over time. And so finding the area under that curve, if we had an equation for this graph, might be doable, or it might be something we would have to do kind of numerically. And more on both in a second. In many situations like this, if we know the equation, we can use integration to find that area under a curve. So when do we need to integrate? Well, in this unit, in Unit 4, we're going to be looking at the net work being done, and that's often an integral of the net force with respect to position, which is when it's non-constant. The work-energy relationship. In Unit 5, we're going to be finding the center of mass of an object using integration, and we'll use the integration kind of method, very similar to the work kinetic energy formula, to find impulse and momentum relationships. A little bit different, but we'll talk about that when we get there. And in Unit 6, we'll find rotational inertia, also known as moment of inertia. So how do we think about derivatives and integrals in their relationship? Well, we know that the slope of a line gives us the next value in our kinematics series of equations, right? We start with position as a function of time, velocity as a function of time, acceleration as a function of time. We're basically taking the time derivative or the slope to figure out what that graph looks like. We also know that we go the other way. We do the area under the curve to get from acceleration graphs to velocity graphs to position graphs. And of course, the big key here is that we are always figuring out the change in the variable above on these graphs. We can do a specific one, right? An object thrown straight up in the air and falling back down. We call integration the antiderivative or inverse function, right? So the area under the curve comes from doing an integral. So if we start with acceleration, which is defined as the rate of change of velocity, we can take the integral of that, and say that the velocity as a function of time is the integral of the acceleration as a function of time integrated with respect to time. And we can do that again in terms of finding the position with respect to time. Now, when we go from acceleration to velocity, velocity to position, we always had to have an initial condition. Sometimes with integration, we call this a side condition, but this is the initial condition for the position in the velocity graph so we can know where to start them. The whole idea behind integration, though, is that we are adding up the little bits of a complicated or not so complicated curved function, something that is not linear, that cannot be defined by nice, simple shapes like triangles and rectangles. And so what we do is we draw a bunch of little rectangles, which are easy to calculate the area of, and we sum them up. Now, in a discrete fashion, the area is the sum of the area of all the rectangles, and each rectangle has a base and a height. In the case of this graph, this might be a force with respect to position, which would be giving us work. And if we had a bunch of discrete rectangles, maybe no more than 5 to 10 of them, it's fairly straightforward to calculate the area of each and add them up. But if we want to be more accurate, we make those rectangles thinner and thinner and thinner. And the thinner they get, the smaller that delta x is, and the more of them we have to add up. And so we get to a place where the delta x becomes arbitrarily small, the limit as it goes to 0, and this becomes the integral. It's a continuous sum. The height of our curve is that force, and the base is the dx, but it's so tiny, it's almost like taking a bunch of individual lines. So that's how we define the integral, where dx is the width of each arbitrarily or infinitesimally thin rectangle. So if the area that we get from our graph is the limit as we sum these up as delta x gets really, really small, we are going to spend some time looking at doing the antiderivative, undoing a derivative or the backwards derivative, and then looking at how we figure out useful values from that. We're not going to talk about why this works. All of that stuff is the purview of your math or calculus course, which you will be, I'm sure, excited to learn. So to find the derivative, as a review, the power rule says that if you have a constant times a variable raised to a power, that the integral of that is still that constant exists, but then the power becomes another constant out front, and the power changes to n minus 1. To integrate, we do the opposite. If you're integrating ax to the n with respect to x, we get ax to the n plus 1. We add to the exponent, and we divide now by the new exponent. That allows you to have something that if you were to take the derivative of it, it would undo that work, which you could try. So here's an example. If our acceleration with respect to time as a function of time is 36t squared, we can take the integral of that, which will be 36t cubed divided by 3, which ends up being 12t cubed, plus a constant. And that constant is what we call the constant of integration, where we are saying there has to be some initial condition. If t is 0, what is the velocity? That would correspond to the initial velocity in this example. You can double check this by taking the derivative and see that you get back to acceleration equals 36t squared. Another example here, if we have the velocity as a function of time, 12t cubed, we can assume that the constant of integration is 0 in this case. And if we do, we are going to get the following: 3t to the fourth, and the constant of integration pops out again in this case, right? So one of the things to remember is that the constant is going to show up every time we integrate, and it's going to disappear every time we take a derivative. So this constant of integration ends up being the initial position of the object. We can again check this by taking the derivative. If the function contains multiple terms, the function of x is ax squared plus bx, we're going to integrate each term separately. So that breaks into the integral of ax squared with respect to x plus the integral of bx with respect to x, which you end up with a over 3x cubed plus b over 2x squared plus a constant of integration. The constants combined, we just have a constant whenever we do this. When integrating trig functions, there are some rules here. I'm just going to quickly show you the two most common that we use. The integral of cosine theta with respect to theta is sine of theta plus a constant. And for sine of theta, it's negative cosine theta plus a constant. You can, again, check them by taking the derivative. So what about that constant of integration? I keep saying that is the initial condition. If you look at these three position time graphs, which are all 1/2 t squared, but one is +0, one is +2, and one is +4, you'll notice that what that does is shift them up the position axis. Basically, they have different initial positions. They all have the same derivative, where the velocity with respect to time is just t, so it's a straight line linear relationship. But how can you know which one of those is the appropriate pair with this velocity time graph? For that, you would need to know some sort of integration, right? If we integrate, we end up getting a plus c, and that plus c is our initial or side condition. And in the case of a particular one, if I tell you it is, say, 4, then that would tell you which one of these graphs makes the most sense, because that plus 4 meters, starting at 4 meters, matches graph number 3. We need that constant of integration in order to say something useful about this. All right, so we want to determine the constant of integration. And so for that, we do our integrand, where and we have a side condition. It may not be the initial condition. Notice this is at t equals 3 seconds. The position is 8 meters, not the same as where are we at 0 seconds. But if we do the integration, take the antiderivative plus a constant of integration, we can say, well, at 3 seconds, the constant would allow our result to end up being 8 meters. We can solve for that, and we find that in this case, c is negative 10 meters. So we must have had our initial position of negative 10 meters. So we rewrite our position as a function of time as 2t squared minus 10. All of those things are indefinite integrals. They're an integral where we take the antiderivative and then we say there is a constant of integration that we may need to worry about. That was something like this. If force is equal to kx, then the integral of the area under that curve is equal to the integral of kx, which is 1/2 kx squared plus a constant of integration. But looking at our graph, we are going to say that the constant of integration is 0, since the force is 0 when x is 0. And that means that we will have 0 work done when we are at position 0. So that allows us to understand our constant of integration. But we can do better than that. Instead of just saying what is happening at the beginning, we can look at a definite section of this integral. So instead of looking for the area of the whole thing, right, from 0 to x, we could talk about integrating just from one position to another, say from x initial to x final, where x initial is not 0. And that's what a definite integral allows us. We can say that x initial and x final are my limits of integration. So this is a trapezoidal shape, one that you don't actually need to do an integral to solve, but we'll use this as an example because it's relatively straightforward, right? How do we find that area? Well, what we're going to do is we're going to find the area of the triangle that starts at 0 and goes to x final, and subtract from it the area of the triangle that starts at 0 and goes to x initial. What that means then is we are going to integrate from, or we were going to do two integrals, and we're going to subtract them, basically. We have a more compact notation for that, and that is this, where x initial and x final are the limits of integration. We're going to start at x initial and go to x final. How does that work? Well, let's take a look. If you integrate from, say, 10 to 20 centimeters here, if that's x initial and x final, we would write the work is equal to the integral of x initial to x final of force as a function of x, with respect to x. Those are 0.1 and 0.2 meters, respectively. And when we take the integral, we get 1/2 kx squared, and we use this square bracket, just the closing of it, to say we're going to evaluate that from 0.1 to 0.2. And because that notation means we're going to do the larger one minus the smaller one, or the top one minus the bottom one, in reality, we end up with 4 joules minus 1 joule, or 3 joules of stored energy or of work done to apply this force over that distance. Another example, we can do this in kinematics, right? What is the displacement from 3 to 6 seconds? So again, it takes that form, integral from 3 to 6 of 6t squared dt. When we take the antiderivative, we get 2t cubed, evaluated from 3 to 6, and that gives us 378 meters. Why don't we have to include the constant of integration? Well, the reason for that is that if it occurs in every integration, every antiderivative here, we end up having plus c and minus c, which goes away. So the only calculus you really need in this course, obviously you need to know how to compute these, but this is the entire total values and things you need to be able to do. We've got a little chain rule in there. We have some particular integrals, power rule stuff. Natural log is in there. There are a few special cases, and we'll talk about them as we get there, but those are the ones you might need.